Welcome to the video for Chapter 9, Lesson 2, Similar Polygons. By the end of this lesson, we should be able to tell if polygons are similar. Of course, let's start with some vocab. A polygon is a closed, flat, geometric shape formed by segments. The segment part focuses on the fact that we should not have any curved pieces to a polygon. So this is not a polygon. We're looking at our regular squares, rectangles, triangles, pentagons, hexagons, and they don't even have to be regular polygons like that. Something weird shaped, again, trying to make more flat pieces here, can be polygons also. The closed part just means that it's not allowed to be hanging open like that. That's also not a polygon. Similar in reference to polygons are polygons that are the same shape but not necessarily the same size. This single squiggly here is the symbol we use for similar, and we will see that several times in this lesson. So polygons that are the same shape but not necessarily the same size. Think about t-shirts. T-shirts are a good example. Now they're not a good example of a polygon because of the curved pieces at the neck, but when we have something that maybe is a shirt that's a size extra small, that's going to be similar but same shape but different size to the exact same style t-shirt, but maybe it's in an extra large. So that's what we're talking about here. They're going to be the same shape but not necessarily the same size. And down here, if two polygons are similar, this double-sided arrow, remember that means if and only if, and that's that biconditional statement again. So two polygons are similar if their corresponding angles are congruent and their corresponding sides are proportional. And so this double-sided arrow means that if you are told that two polygons are similar, then that means that their angles are congruent and their corresponding sides are proportional. But it also means in the opposite direction that if you know that the sides are proportional and angles are congruent, then the polygons are similar. So let's take a look at these two triangles. This statement up top says triangle ABC is similar to triangle DEF. So let's take a look at what that means as far as these measurements are concerned. Notice that the angles that are marked congruent are angles A is congruent to angle D. And again, we're just using these congruency tick marks. We have a single arch, and then angle B will be congruent to angle E, and angle C is congruent to angle F. And we are very familiar with these markings for congruency. What might be more new, however, is this idea of proportionality with the sides. So we're going to compare the corresponding sides. So from the single tick mark to the triple, we have a 4 to an 8. And then from the single to the double, we have a 5 to a 10. And then the last side we have, let me change that to red, we have a 6 to a 12. And the question really is that we're going to be looking at here is, are these sides proportional in the fact that do they simplify down to the same fraction? And in this case, they do all simplify to 1/2, which means the sides are proportional. So this is what we're going to be looking for. Angles, congruent angles, proportional sides. That's what we're going to be having within our similar polygons. In this case, we're just looking at triangles. Now, one thing we need to realize is that you may not always have the numbers here, or we could also be using the letters here, stating that, side AB in relation to side DE is equal to side BC in relation to EF, and last side CA in relation to FD. And so all I did is I worked my way around the triangles there, AB to DE, BC to EF, CA to FD. And that's where these numbers are coming from. These fractions should be equal because that's what it means to be similar. This first example is determining if the pair of polygons is similar. And remember, we are checking to compare if angles are congruent and if sides are proportional. And if we look very quickly, both polygons have 4 right angles, so we can definitely say that the angles are congruent. They are all 90 degrees. So we have congruent angles, so that part is done. Now we move on to the sides, and we need to compare the big rectangle to the small rectangle. Now we cannot assume just because they're both rectangles, and yes, technically they are the same shape, but not the same size, we cannot assume that they are actually proportional. So we need to check using our proportion equations. I am going to compare this 4 side, let me grab a different color, the 4 to the 2, so that's going to be my first fraction, my first ratio, and my second ratio will be this 8 to the 3. So I'm going to compare 8 to 3, and the question is, are those two fractions, those two ratios equal? And we could try to simplify them. The 4 over 2 does simplify, the 8 over 3 does not, so that should be a big hint right there. But another check, just as a reminder, is that cross products should be equal in proportional relationships. So this 4 times 3 is 12, 8 times 2 is 16. They do not equal each other, so there is not a proportional relationship between the sides, so they are not similar. So not similar polygons. And again, this is a very good example of just because they are the same shape, they are both technically rectangles, that does not guarantee that they are similar. This next problem seems to be comparing parallelograms. Opposite angles are congruent, and within that, they are congruent to each other in the different, from this polygon to this polygon, this parallelogram to this parallelogram, they are angles congruent. So we definitely have angles congruent, so we can check that off the list. Now, if we move into the sides, again, checking for proportionality. If I check this 3 with the 6, that will be my first fraction, my first ratio. We need that to be equal to this 7 over 14. So 7 over 14. The question is, do those fractions equal each other? And we can simplify them. 3/6 is 1/2. 7/14 is also 1/2. So, oops, 1/2, not 1/14. So they do equal each other, so they are proportional. But just to prove the cross products, again, to make sure that you understand where I was coming from with that last problem, the cross products do equal each other. 3 times 14 is 42. 7 times 6 is 42. So if the cross products equal each other, that proves the proportional relationship. And obviously, if the ratios simplify down to the same fraction to begin with, they are also proportional. So we would say yes, they are similar. Next type of problem would be finding x and y that will make these polygons similar. Remember that in these cases, we just assume that they are similar, and that would help us find the missing values. Now, what's going to be tricky about this is which proportions to set up, because you can't have an equation or one proportion equation that has an x and a y in it. And if you look at this example, this side right here has an x and this one has a y. So we have to make sure that we're not picking ratios where the x and y are in one proportion equation at the same time. We do have a 5 that matches with the 3y minus 2, so we're definitely going to use that with the 3y minus 2. The 10 matches with the 20, so that's something we can use consistently, and there are no missing pieces there. A 10 and a 20, they are the corresponding sides there. And then the x plus 3 matches up with the 12, so we should be able to use that ratio of sides to find the value for x. So let's take a look at what these two proportion equations would look like. So let's take a minute to make sure we understand this. 10 over 20, so I'm going from the left to the right. 5 over 3y minus 2, left to right. Again, then with the 10 over 20, left to right. X plus 3 over 12, left to right. And these portion equations we would solve. So solving gives us that the y value is 4 and the x value is 3. I'd like you to pause the video right now and see if you can set up these proportion equations yourself, paying attention to your variables, left to right, big to small. Go ahead and set that up. So I went left to right again, big to small. The 15 and the 10 are on corresponding sides, so I use that as my base ratio, 15 to 10. Then the x matches with the 6, and the 5y minus 3 matches with the 9. So we can solve these proportion equations for x and y. This answer did give us a decimal for the y value. I double checked to make sure that I set it up all correctly. I did solve correctly, so even though it is a little concerning that I got a decimal answer, it is possible. Decimals are numbers too. Moving into applications here, these of course are going to be word problems. There is going to be kind of expected level of common sense, world sense. So like this problem here is going to be about blueprints. There are lots of proportional relationships with maybe scale models, missing heights of buildings or tall things in relation to the height of like a person and a shadow, maybe recipes or mixing ratios for paint, lots of different options for comparing two things, because that's really what a ratio is. So I'm not going to overwhelm you with examples here. I just need you to understand that these examples are certainly not the end-all be-all to the way proportions can be used. So the blueprint says 1 inch represents an actual length of 16 feet. So 1 inch to 16 feet. Now, if I was simplifying this down to a simplified ratio, I would need to worry about the units. But in this case, we are making a connection between the smaller blueprint on the piece of paper, so the inches, to the actual structure, which is going to be in feet. So I'm gonna leave it as inches and feet. And when we are talking about dimensions of a room, there are two measurements. 2 inches would be maybe the length, and then the 1.5 inch is the width. They do not go in the same problem. They need to be solved separately. So the 1 inch representing 16 feet is great. So what does 2 inches represent? And this is the proportion equation we would be solving for that. Okay, for the 1.5 inch side, okay, 1 inch still represents 16 feet because it's the same blueprint. But now, well, then how much is 1.5 inches going to represent? And this is an important skill. I'm gonna make this a Y. This is an important skill because there are lots of times that you may actually be looking at a blueprint or some sort of scale model. Lots of professions require this sort of skill. So I'm going to cross multiply, X equals 32 feet. And I know that my label is feet because that's what's next to my X right there. And then in my Y value, it's gonna be Y equals 24 feet. So if you are looking at a blueprint that has a square or a rectangle that's 2 inches by 1.5 inches, then that room in real life would be 32 feet by 24 feet. The next problem is actually more interesting because it actually represents the first step. A blueprint generally comes after someone already knows how big they want something to be. So how big would the blueprint figure be if the actual room was 5 feet by 12 feet? Maybe we need a room to be that specific size for a specific reason, so we have to work backwards. So we're looking at it's still the same problem because it's just a sub-problem of the information. So I still have 1 inch representing 16 feet, but now the question is, okay, well, how many inches will I draw the 5 foot line? Okay, if 1 inch represents 16 feet and I have a 12-foot room length, how long am I going to make that line? And these are the two proportions that we solve for our inches. Notice that with these answers, I am leaving them as a fraction because fractions make more sense when we are talking about measuring in inches. So 5/16 of an inch and 3/4 of an inch. Problem B is a good example for finding the height of taller objects. It says Scott is standing near a flagpole on a bright sunny day. The shadow of the flagpole is 10 feet long at the same time that Scott's shadow is 2 feet long. We know that Scott is 6 feet tall, so how tall is the flagpole? So let me do a quick drawing. So these pictures represent the flagpole and Scott, and then the length of their shadows with their heights. And the height of the flagpole is what we are missing, so I labeled that an H. Now, what we do have here are two right triangles. They are similar because they are happening at the same time, and that's why this part is mentioned, because if they weren't at the same time of day, then the shadows are going to be different lengths. But when they are the same time, then the sun is casting the same shadow relationship in the same way. So we can set up these this similar relationship where h to 6, so the height of the flagpole to the height of Scott, the shadow of the flagpole to the shadow of Scott. And there are lots of different ways we could set this up. Like we could have the height of the flagpole to the shadow of the flagpole, the height of Scott to the shadow of Scott. Like this is not the only proportion equation we could set up to solve, but there are also relationships that don't work. So solving this, we get h equals 30, so the flagpole is 30 feet tall. So far, the problems have been triangles, quadrilaterals. It didn't matter. They were just polygons in general. But there are, of course, similarities specific to triangles simply because of the properties that triangles do have. So let's take a look at some of them. First one is by angle-angle similarity. So if two angles in one triangle are congruent to two other corresponding angles in another triangle, then the triangles are similar. We also have side-angle-side similarity. So if two sides are proportional and the included angles are congruent, then the triangles are similar by side-angle-side. And last, the side-side-side similarity, which says if the measures of the sides in one triangle are all proportional to the measures of the corresponding sides in another triangle, then the triangles are similar. We did really already have this concept of similarity previously. This is just specifically as it applies to triangles. And using those similarities actually allows us to write a similarity statement, much like our congruent statements back from a previous chapter. So first thing I'm going to do is I'm going to check to see if I actually do have proportional relationships here. So the 24 with the 18, the 28 with the 21, and the 20 with the 15. These are the proportional relationships, the ratios that I will set up, and I am going left to right, and I have to be consistent with that. 28 over 21, and then 20 over 15. And again, the question is, do these equal each other? Okay. And if they do, we can say that the triangles are similar. Simplifying these fractions, 24 over 18 simplifies down to 4/3 by dividing by 6. 28 over 21 also simplifies to 4/3 by dividing by 7. And 20 over 15 also simplifies down to 4/3 by dividing by 5. So since they are all equal to each other, all three sides are proportional, so we can say that triangle ABC is similar to triangle UTV by side-side-side similarity. And again, just like our congruent statements, your order does matter. A, B, C needs to be UTV. In looking at this example, it looks like we have congruent angles here, and we also have congruent angles at N and J. And two angles are all we need for angle-angle similarity. So I'm just gonna write by angle-angle similarity because I know that that's what I'm going to use. The question will be, where do you want to start? So I'm going to start with the 2 tick-marked angle and say triangle N, and then I'm going to follow it down to K and then out to M. So NKM is similar to triangle, and I pointed this out because it matters now how we go orders for this triangle. So I started at the 2 and I went to the K, which was 1. So with this triangle on the right, I have to start at J and then go into K. So triangle JKL would be my last vertex for the triangles, for naming it. So triangle NKM is similar to triangle JKL by angle-angle similarity. Final example is of that final similarity, which would be our side-angle-side. If we look, we have 8 and 12 should match. We have our included angle of 35 degrees, which are congruent, and then the 10 and 15 are corresponding. We're going to check to make sure that 8 over 12 does actually equal 10 over 15. again, a question mark over that. And so we're either simplifying the fractions or we're cross multiplying. I'm just gonna simplify here by 4 to get 2/3, and then by 5 to also get 2/3. So the ratios are equal, the triangles are similar. They're not congruent because remember guys, congruency is the exact same size. It's moving or recreating the triangle without movement. These are different sizes. These triangles just happen to be similar. This would be like a triangle on a size small shirt. This would be a triangle on a size medium shirt. That triangle has to grow, but in a proportional relationship so that it looks like the shirts are actually the same. So either way, our similarity statement is triangle OGD. So I went from O down my purple side and then out my green side. So OGD is similar to starting at A, triangle A, down my purple side, and then out my green side. So ATC by side, angle, side, similarity. These last couple problems are just more examples with triangles. There's a word problem and then 2 just diagrams of triangles. So I just wanted to put these on here for a little bit of extra practice. Please go ahead and read through them, try them on your own. I'm not going to be talking through these. I'm just going to be putting up the work and the answers. So if you have questions, please make sure you ask. This concludes the video lesson for about similar polygons from proportions and similarity. So how can we tell if polygons are similar? Similar polygons have congruent angles and proportional sides.